Okay, thank you so much. Hi, everybody. Welcome to your first class in these trends in cryptographic protocols. So in this sequence of lectures, you will be presented with a sequence of cryptographic tasks, such as zero-knowledge proofs, private set intersection, private information retrieval. And for each task, we will give you a definition of what it means for the task to be secure, and then we will show you a construction, and then we will show you some formal proof of security. Now, the purpose for this class, and this is lecture 1, is to kind of establish the foundations. So as you will see in the, you will see that along the classes, you will find definitions such as experiment, security game, simulator, indistinguishability, and all these concepts, they all make sense once you understand what are the reasons why we write security definitions the way we do. So this class, it's actually your opportunity to understand where are those definitions coming from, why we are thinking of a security game, why in cryptography we talk about distinguishers, what is the concept of a simulator. You're going to also hear the concept of ideal world and real world, and that can be confusing. And you might ask, okay, what's the point of talking about ideal world and real world when I'm trying to prove security of a cryptographic scheme? So the idea for today is to really build your intuition and your foundations on what it means, what is the meaning of a cryptographic security definition. Okay, so let's start. The first question is why we care about formal definitions. And the answer is, if you don't have a formal definition, you cannot have a formal proof of security. What it means that if your security definition is just something, a sequence of words, then probably your security proof is going to be just a sequence of words. And it does not give you any guarantee that your scheme, it will be secure with respect to any attacker. So the reason we put formal definitions in place is because we want to be able to write formal proofs, and we want to be able to write statements to the effect of saying our scheme is secure no matter what the adversary does, so long that the adversary runs in polynomial time. So we only put a computational bound on the adversary, but nothing else. Okay, so in this lesson, I'm going to build your knowledge around how you write a formal security definition for a cryptographic protocol. Okay, and in order to do this, I'm going to start from something that is not a cryptographic protocol, but is a cryptographic primitive. And I'm going to start from the concept of security of an encryption scheme. Okay, so we all know what encryption scheme is supposed to do. All right, so let's start with the task that we all know about, which is the task of encryption, right? Now, in this task, you have two parties, Alice and Bob. They trust each other, so they are both going to follow the instructions without a problem. Their goal, however, is to communicate over a channel that is compromised. So over the channel, we have this red eye here. This is the adversary. In this case, the adversary is just an observer. And the adversary observes a bunch of ciphertexts going back and forth from Alice and Bob. And of course, the goal of the adversary is to learn what Alice and Bob are going to talk about. Okay. Now, if we think of an intuitive definition of security for an encryption scheme, we will probably say, well, for an encryption scheme to be secure, it's necessary that from the ciphertext, the adversary can learn no information. That's a good definition intuitively, but then the question is, what does it mean to learn no information? What does formally means to learn no information? And typically in classical security proofs, if you have a scheme, in classic cryptography, we will just say, well, this scheme is secure because it withstands all possible attacks that we know of. But then the question is, what about attacks that you don't know of, right? So that's when we move from classical cryptography to modern cryptography. And in modern cryptography, we actually, our goal is to really formally define what it means that a ciphertext leaks no information. How do we formally say so? And then once we have a formal definition in place, then the next step is to show, to prove that a certain scheme achieves that definition. Okay, so let's start with the simple example of an encryption scheme. How do we define that an encryption scheme leaks no information? This is defined through a security game. Okay, so we model this game as two parts, where an adversary, in the first part, the adversary plays the game by interacting with an encryption oracle. So we have here the adversary, and the adversary has access to as many ciphertexts as they want. And the idea here is that in real life, we are capturing the power in the real life that the adversary can always have an idea of what are the messages exchanged between Alice and Bob. So here we are capturing the observing power of the adversary. Then in the challenge phase, there is a second phase we call the challenge phase. The adversary is challenged to tell us if it's able to learn any information from the ciphertext on which the message is not known in advance. So in the challenge phase, the adversary sends two messages to a challenger and receives the encryption of one of them. And the message that will be encrypted is chosen at random. And the goal of the adversary is to guess this bit. Okay, so here we say that we say an encryption scheme is secure if the probability that an adversary can actually guess the message encrypted in C star, it's not better than half. Okay, so you can see that in this challenge phase, we are actually capturing this no information thing, right? So if the adversary cannot even tell which message is encrypted in C star, even though the adversary chose the messages M0 and M1, then this guarantees that the adversary is not learning anything about what's encrypted in C star. Okay, so this is kind of a picture definition of it's like a description of what more formally is described the CPA secure security game, which you can find in the old books of cryptography. And basically, when we define the security of an encryption scheme, we say that an encryption scheme is secure if for any probability, let's see if I can annotate here. Yes, spotlight. So if for any probabilistic polynomial time adversary A, the probability that the adversary wins the game is at most 1/2. Okay, so let's go back for a second here. What I want you to take out of this slide is the following. The way we capture that the adversary does not learn anything is through this challenge phase. If the adversary is not able to guess which is the message is encrypted in C star, then I can say that C star is secure. Like the encryption scheme used to compute C star is a secure encryption scheme. Now, this is a very simple example where the adversary really is passive, is just observing. However, this idea, we can use the same approach now to think of how to model security of a cryptographic protocol. Okay, so let's now move on to a cryptographic protocol. So the first difference now between the encryption scheme, which is a cryptographic primitive, and a cryptographic protocol is that a cryptographic protocol is executed between two parties who are not trusted. They don't trust each other. These two parties here in this picture, we have Alice that has a secret input X1. We have Bob who has a secret input X2. And then we have the goal for Alice and Bob is to run a protocol to learn an output Y of X1 and X2. The main goal here in a cryptographic protocol is to make sure that the protocol only leaks the output of the function and nothing else. A typical example of such of a function for which you want to run such a protocol is the millionaire problem. So you have two millionaires and they both have a certain amount of money and they want to learn who is richer. In that case, they can run a protocol, and the output of the protocol is just a bit to tell if Alice is richer or not. Okay, so we really want from this protocol that the messages of the protocol, which is called transcript, the transcript of the protocol should not leak any information about the inputs, but just the output. Okay, so in the second part of this lecture, my goal is to show you how we go about defining security for a cryptographic protocol. Now, let's start with a very specific cryptographic task, which is the task of proving knowledge of a secret. So now let's look at the case of a zero knowledge proof, where you have a prover and a verifier. They don't trust each other. So we will have, from now on, we'll have a setting where the adversary is one of the parties. Okay, so they don't trust each other, and one of the party is trying to convince the other party that they know a secret. Okay, so let's look at these concrete examples where we have on the left side a prover, Satoshi Nakamoto. We have some party, they want to prove to a verifier, which is malicious. They want to prove that they know the secret key, that they are Satoshi Nakamoto. Now, for those of you who, I'm sure everybody knows who is Satoshi Nakamoto, but it's the owner of the Bitcoin wallet associated to the first Bitcoin wallet of Bitcoin, right? So now let's say we want to create a protocol that allows a party to prove that they are Satoshi Nakamoto. How would we do that, right? And what would we need from this protocol? Now, if we didn't have a formal definition, we will say informally, well, Satoshi can just sign a message, and that will be enough to convince a verifier. If the signature verifies under the public key of Satoshi, this will be enough for the verifier to be convinced. And this signature is coming from Satoshi Nakamoto. Now, this is a great protocol to prove identity, right? However, this is not enough to, this is not a protocol that does not leak anything, right? So if we give a signature to the verifier, we are leaking something, because now the verifier, before running the protocol, the verifier did not know anything. But now after running the protocol, the verifier knows a signature, okay? So that's the peril, that's the risk that you run into if you don't write things formally. So if I just stop and saying, well, the protocol should not leak the secret key, so I just sign, that's just intuitively correct. But if you go formally, you will notice that this protocol does leak a signature. So we don't want that, right? So our goal is here to have a stronger security. So we want that the verifier learns nothing besides yes or no. So we want to say a protocol for proving knowledge of a secret is secure, so it's zero knowledge, if the verifier learns nothing besides being convinced that the prover has the secret that he's claiming, okay? So now the question is, now that we know what we want to define, how do we formally define the idea that a malicious verifier here on the right should not learn anything from the transcript of the computation? I'm going to stop for a second, and I would like you to think for a second of what we said about encryption. When we talked about encryption, we had the same problem. We wanted to capture the fact that an adversary, by looking at the ciphertext, cannot tell what is the message encrypted. And so there was a challenge phase where the adversary had two choices. One where the message encrypted is M0, and one where the message is encrypted is M1. And the adversary had to figure out what choice was made by the challenger. Now here, we want to kind of replicate the same concept for a protocol, for a zero knowledge protocol. And now instead of a ciphertext, we have a transcript. So let's think about what will be what the adversary needs to guess, and what does it mean to have no information, to learn nothing besides 0 and 1. Okay, so I hope you thought about it a little bit on your own. Let me tell you how we do it. So to provide a formal definition, we have this adversary here, which is our distinguisher. Look at the red die is our distinguisher. And the distinguisher obtains a transcript. A transcript is the sequence of messages of the protocol, of the zero-knowledge protocol. And now, just like the CPA game, the adversary needs to guess how was this transcript computed. Okay. Now, on the other side of this line, there are going to be 2 bits. That is going to be a challenger. And if the bit is 0, the transcript was computed using by Nakamoto, by the real prover, using the real secret. Okay, to prove that the public key, the real secret associated to the public key. If the bit is 1 instead, the challenger is going to compute this transcript using something that we call the simulator, and without knowing any secret. So see, if B is equal to 0, the transcript was computed with the knowledge of the secret. If B is equal to 1, the transcript is computed without any knowledge of the secret. And then we ask, is there any distinguisher that can tell how the transcript was computed? Now, the idea is if the distinguisher cannot tell, by looking at the transcript, cannot tell how was the transcript computed, then it must be the case that the transcript does not leak any information about the secret, because the simulated transcript was not computed with the secret. Okay, so here I ask the question, why does the definition correctly capture the concept of zero knowledge? It correctly captures this concept because really, if I cannot tell how the transcript is computed, definitely I am not learning if the secret was used or not, right? So I'm not learning anything about the secret. Now, let's pause for a second with this slide. Now, the beauty of this definition, it tells you right away that, one of the transcripts was computed without any secret. So it must be the case that if this transcript is indistinguishable, it must be the case that the protocol is such that nothing is leaked through the protocol. Okay, so this is how the formal definition look like. I don't know if you ever encountered the zero knowledge proof, the zero knowledge definition, but this is how it looks like. And whatever I wrote here in terms of, this red eye here, this is a distinguisher, and these 2 transcripts are 2 distributions, right? And this is what the definition says. There is a simulator, there is also a honest prover, and we say that an interactive protocol is zero knowledge if the view generated by the simulator are computational and distinguishable from the view generated by the honest prover. Okay. Now, you probably are a bit confused at this point because you're saying, well, if this protocol, if a simulator can provide the same transcript without knowing the secret, very likely this protocol is not correct, because if people can just prove it without a secret, then we're not really achieving the correctness, the soundness property. Now that would bring us to the concept of a simulator. So a simulator is a concept that does not exist, is a machine, is a concept that exists only in the proof world. So in the world of definitions and proofs, there is this machine called the simulator. And the way the simulator worked is by rewinding the adversary. And by using a rewinding of the verifier, the simulator is able to compute a transcript that looks indistinguishable from the real world prover. Now, you don't really have to understand what rewinding means, but you do want to just get out of this picture, you want to get the fact that the simulator is a machine that has more power than a real world party. And typically the power we give to the simulator at this stage is rewinding the adversary. By rewinding the adversary, the simulator can extract information that it needs to simulate the protocol. The other thing that you need to know is that to achieve such a definition, the zero knowledge property, and to build this simulator, we need to make some adjustment to the protocols typically. For instance, we know that you cannot have zero knowledge with 3 rounds. So if you want zero knowledge protocol, you need at least 4 rounds. So in order to achieve this stronger security definition, we need the protocol to be more complex. And this is something I want you to be aware of, because as you will see in the next classes, we will construct protocols that seem very complicated. And the reason they are more complicated than you think they should is because that's the only way we can provide a formal proof with a formal simulator. All right. So now this example I just showed you was for zero knowledge. And in zero knowledge, you have a prover and a verifier, and there is only the prover having a secret input. But the exact same idea works for general two-party computation, and that's where I'm going here. So the exact same definition with the game, there is a transcript, there is a distinguisher, but now the only difference is that instead of putting a prover here, we are just putting a party, say Alice, that has any arbitrary input x1. And then on the adversary is a party 2, and they also run with their own arbitrary input x2 or x star. So the reason x is not here is because the adversary does not need to commit to any input in particular. It can run with malicious inputs. And now here, this is important. Here, remember, in the zero knowledge proof that I showed you, the simulator was running with the public key as input. Here, in the two-party computation setting, the simulator will run with y in input. Why are we giving y to the simulator? Because remember, in a secure two-party protocol, we want to say that a protocol is secure if the only thing that is learned by the adversary is the output, y. So that's what we're giving to the simulator. The simulator starts by knowing the output, and it's able to compute the transcript. Now, this is not 100% correct, because when the adversary is malicious, the simulator might need to do some work in order to get this output. But for now, don't worry about it. The only thing you need to know is that for secure two-party computation, the definition is the same as in zero knowledge. The only difference is what are the inputs and outputs of the simulator. All right. So far, let's see how we're doing with time. Okay, we have at least 8 minutes. So far, I hope you understood at least the principle behind the concept of a security definition and the concept of indistinguishability, right? So every security definition is based on the fact that security stems on the fact that the adversary cannot distinguish if we are using the real input or not. And if the adversary cannot, it means that the protocol is actually secure. Now, the definitions I've given you so far, I just put you, there was an adversary, there's a party A and party B, Alice and Bob, and the adversary might be Bob, but that was the only thing that was happening, right? But now the next question is, what if instead of one protocol, there are two protocols in parallel? Right? So let's say, going back to the concrete example of proof systems, right? Let's say I have Bob, the adversary, the malicious verifier. On one hand, he's playing with Nakamoto as a verifier. But then in parallel, the adversary also starts a new execution of a proof system with another verifier, which this time is honest. Now, what can we do now? What can we say about the security of those two protocols, right? So informally, we would like to say that if the protocol on the left is zero knowledge, then the adversary should not gain any information by running on the left here, should not gain any information for the protocol on the right. That's what we would like to say. And now the question is this true? Is it true that if a protocol is zero knowledge, automatically it remains zero knowledge when the adversary is playing two executions in parallel? And the answer is no, really. The zero knowledge definition does not say anything about other executions. It only says if you have one prover, one verifier, the transcript is zero knowledge. Now, if the verifier starts opening many executions, we don't know what happens. So now if you have to target this specific attack, we will need another definition, which is actually called non-malleable zero knowledge. And I don't want to go over the details of it. But I just want you to see that now things become more complicated, because now you have a simulator on the left, the simulator on the right. Just the definition becomes itself, just writing the definition is more complicated. And even creating a protocol that is non-malleable zero knowledge is way more complicated than just creating a protocol that is zero knowledge without, without double executions. So what are the observations that we should make at this point? The definitions I've shown you so far, they seem like we need to change our definition depending on our setting. So we really need to be careful. And now, if I just expand the setting to have 2 parallel executions of the same protocol, I just showed you that now I have to think of a non-malleable definition. But now the next natural question is, what if now the adversary is going to run many protocols which are not zero knowledge proof, like arbitrary protocols? So let's say I have an adversary who is running a private payment protocol with Alice, and in parallel is running a private set intersection with another party, and in parallel is going to run an authentication protocol with another party. So the question is, okay, now what do we do with the security definition I've showed you so far? And that's the challenge. That's what happens when we start talking about concurrent execution of secure protocols. If we start worrying about that setting, then we need to think of a completely different approach for definitions. Why? Because if I'm going to assume that the adversary can run as many executions as they want with as many protocols of different nature, definitely I cannot create a new definition for every possible combination. So that's where the concept of universal composability model comes in. You can already tell from the name, universal composability. It's a completely different framework that was introduced in the 2000s by several people, and they kind of came up with it at the same time. And their approach is slightly different. It's still based on the indistinguishability of 2 transcripts. However, their framework tried to take care of all the executions that are taking place by capturing with the concept of environment. Okay, so let's see what are the elements of a universal composability framework. There is an environment. What is an environment? The environment is a machine, and this environment captures the fact that the adversary could control many protocols execution at the same time and can control the inputs of the parties of such protocols. So we capture all those executions under the concept of the environment. The environment in this framework, the environment also chooses the inputs that the honest parties need to play with. So we kind of give a lot of power to this environment. Then we have the concept of an ideal functionality. So if you are trying to, for instance, create a zero knowledge proof system in the UC framework, you will have to write down an ideal functionality. What does ideal functionality mean? It means you are going to describe what you want from your, what are the security properties you want from your protocol by imagining that there is an ideal functionality that gives you that property. So in the case of zero knowledge proof, what is the property we want? We want that the prover knows the witness and a verifier is convinced, right? And nobody has to learn anything. So the ideal functionality that we can think of is a functionality that takes an input, a witness from the prover, checks that is good, and just give an output to the verifier saying, oh, I checked, it's good, right? So that's an ideal functionality. It's called ideal because it does not exist in the real world. But we define that ideal functionality. And then now the simulator here, it's supposed to interact with the ideal functionality. And the goal of the simulator is to create a transcript that is indistinguishable from a real prover, even though the simulator is only talking to the ideal functionality, which basically means the simulator is not getting any information besides 0 and 1. Okay, so we are back to the, so here we are really back to the transcript indistinguishability definition. Is almost the same idea. So you have a distinguisher here, you have a distinguisher here, you have a simulator. The simulator is interacting with an ideal functionality, and the distinguisher needs to check if this transcript is coming from a real party interacting with the adversary, or from the ideal functionality interacting with the simulator. Okay, so this is very similar to what we said before. The difference now, though, is that this distinguisher here is not passive at all. This distinguisher has access to an immense amount of information, and the simulator is not aware of it. So this is kind of the beauty of this framework. We can prove security of our protocol without having to know what is the distinguisher doing. So how many executions are running? Okay, and I put this. I put this kind of this. I blank on the name of this animal, but anyway, I put this this here to show, you know, that you can think of this this distinguisher, this environment having a lot of tentacles and being connected to a lot of things going on in the world, or the simulator does not have to be aware of it in order to simulate. All right, so this is an example of how an ideal functionality looks like. This is the ideal functionality for non-interactive zero-knowledge proof. And you'll see the functionality takes an input from the prover. It takes a witness and a statement. In this case, they call it Y. And the verifier just, in this case, the verifier also gets some information phi. But the idea is that the ideal functionality checks the witness and gives the answer to the verifier. All right, so it seems magical, right? What I just explained, to you, it seems magical. Like, okay, this UC framework, now all of a sudden the simulator can do everything without having to know what the distinguisher is up to. So it's good for the proof. Like this, the UC framework is very elegant to use and to write proofs in. However, it comes with a big price. The price is that now the simulator, in order to simulate the transcript correctly, cannot rewind the adversary. So the only way for the simulator to be successful is that we give some trapdoor to the simulator. So we need to cheat in some sense. So whenever you see a zero-knowledge proofs or oblivious transfer or PSI, whatever you see something in the UC framework, very likely you are using an assumption, a trusted assumption. So you're assuming that the system is based on some parameters that are trusted. And this assumption helps in the pure proof of security, because in the proof of security, we can assume that the simulator, which is just a mental object, the simulator has access to trapdoors that in the real world, real parties don't have access to, because in the real world, a trusted party will never give access to this trapdoor. So you can see that when we use the UC framework, we are gaining in security, like we are giving a proof of security which withstands any possible composition. However, at the same time, we are losing in that now the system relies on the security of these trusted parameters. And if these parameters are not trusted in real life, then we lose basically everything. So that's something to be aware. There's something we should be aware of as you go through these protocols along the line. And but also don't worry, there are ways to potentially distribute the computation of these trusted parameters using multi-party computation. All right, so this concludes my presentation, and I think I'm a little bit over with time. So I would like to just give you open the stage for questions.